Welcome. Today we will be discussing the relationship between force and time when considering a person's total momentum. As seen in this video, Batman is extracted from a building via a C-130 airplane. Now,
the Lockheed MC-130, the plane used in the Dark Knight, is used in the United States military for extraction program called the Fulton Surface-to-Air Recovery System. The Fulton Surface-to-Air System is the system used by the CIA, United States Air Force, the United States Navy for retrieving persons on the ground from aircraft. The system was developed by the inventor Robert Edison Fulton Jr. for the Central Intelligence Agency in the early 1950s. The insurance safety department now uses a braided nylon line with the test strength of 80,000 kilograms.
The AC-130 is one of more than 30 versions of the Hercules. Another is this MC-130 Combat Talon. It can pick people up off the ground or the sea without landing, people like James Bond, you may remember. But this demonstration of the Fulton Surface-to-Air Recovery System is not in a film, it's for real, although it's so uncomfortable that it's only done with dummies except in real emergency.
like we mentioned earlier, we will be calculating the force and the change in time. The equation that we will be using is the impulse equation of delta t equals m delta v. This is one of our equations in the momentum unit. Batman starts from rest and accelerates at a constant rate. The plane has a constant velocity and extracts Batman off the ground and into the air. What we want to figure out is if Batman would survive this extraction, and we also want to look at the different times and forces that can be exerted on him.
Alright, so let's do some calculations. In our project, we will be using the impulse equation, which is F delta t equals m delta v. This is explained as the force exerted on an object times the amount of time the force is exerted is equal to the mass of the object times the change in velocity of the object. So in this equation, we know that the mass of Batman is equal to around 90 kilograms. The change in velocity of Batman is equal to the typical cruising speed of the plane, which is about 8,033.3 meters per second. So, in our equation we know that F delta t is equal to 90 kilograms times 8,033.3 meters per second. So, F delta t is equal to 722,997 Newton seconds. So in our problem, we now know that the change in momentum of Batman is equal to the force exerted on Batman multiplied by the change in time the force is exerted on Batman. We know that both of these are now equal to 722,997 Newton seconds. So, in this equation, as the force exerted on Batman increases, it is known that the change in time that the force is exerted over decreases. And likewise, as the force exerted on Batman decreases, the change in time this force is applied over increases. So viewing this graphically, we know that on the graph of force versus time, change in time rather, the area under the graph must be equal to this value here. So let's say that we have a low force equal to x and a large time equal to y. It is known that this area under the graph here must equal 722,997 newton seconds. However, if we increase this force, let's call it 2x, then the time would have to be cut in half. So we would only have 1/2 y. And under this graph, the area would also be 722,997 newton seconds. Okay, so from our previous calculations, using the kinematic equations and finding the force of a 90 kilogram man falling 4 stories, we know that a lethal force for Batman would be around 13,809.6 newtons. So, if that is a lethal force, and we want to calculate the amount of time that this could be, this force could be exerted over, we would use this F delta T, or the change in momentum, or impulse, it's like T rather, is equal to 722,997 newton seconds. So, this force is known to be 13,809.6. This would be the maximum force Batman could have exerted against him, so that would make the minimum time equal to 722,997 newton seconds over 13,809.6 newtons, which is equal to that is equal to 52.35 seconds. Okay, so as we found using that last equation, we know that maximum force Batman can encounter in the minimum amount of time is equal to 52.355 seconds, and the maximum force he can encounter is 13,809.6 newtons, because this would be a lethal force, or near lethal force, assuming it doesn't kill him, and this would be the least amount of time that such a high force could be exposed over, because this is our maximum force, so it produces our minimum time, because they are inversely related. So now we'll look at seeing what kind of force could be applied if Batman wanted to be perhaps more comfortable and have less of such an impacting force applied on him. So what will change is, in our impulse equation, is the force here, because if you have a smaller force, it's going to be more comfortable for the person. So let's lower this from 13,000 to say 10,000. So now our equation looks like it will still be F delta T is equal to 722,997. And this is the same because we're not changing our change in velocity or the mass of Batman. So these are still constant. These are the only variables that we're changing. So if F now equals 10,000. Then we have the equation delta T equals 722,997 newton seconds over 10,000 newtons. So we get our delta T to equal 72.2997 seconds. Okay, so from that last equation we used, we know that the maximum force Batman can endure is 13,809.6 newtons, and that puts out a change in time of 52.355 seconds that this force has to be exerted over. So we changed it to 10,000 newtons, and we found that the change in time had to change also to 72.2997 seconds. So the force went from being a larger force in the first example to a smaller force in the second example, and therefore the change in time went from a smaller time in the first example and a larger time in the second example. This shows that these two, force and change in time, are inversely related, and it shows that when going from a larger force to a smaller force, the time has to also change from a smaller time to a larger time. Okay, so to recap, let's just view this graphically one last time to see how these forces and times are inversely related. So in our first example, our force was about 13,809.6 newtons, which would put on the force scale right about here. And with that, the change in time was about 52 seconds. So drawing this roughly, this graph would look about like this. So we know that the area under this curve is equal to F delta T, which is 722,997 newton seconds. In our second example, we lowered the force to about 10,000, which is right here, and that put out a time of 72.2997 seconds. So that'd be about right here. So if we drew this, it'd be about right here. And in this case, the area under the graph would also be equal to 722,997 newton seconds. So as we can see here, as the force, just to recap once again, as the force here decreases, it forces the time to increase. So as force increases, delta T decreases, seen from example 1 to 2. And likewise, as the time increases, we see that the force decreases. So, based on our data and our calculations, we can conclude that the forces seen in Hollywood films such as The Dark Knight and the extraction seen in this movie would be plausible if this force was exerted over the correct amount of time.